All right, in this lecture, we will discuss how to estimate the diffusion coefficient. Our goal is to estimate the diffusion coefficient. EAB for a solute A in aqueous solution B. In liquid B. So the equation or the model we are going to use is called the Stokes Einstein model. And Stokes is one person, Einstein is another person. And they both contribute to the half of the equation. So this estimation depend on several assumptions. So first of all, we recall that it's a dilute liquid solution. And also we assume that the solute is a solid spherical particle. Is solid spherical particles. And also for the diluted liquid solution, we also assume it's continuous. And also the solute is significantly larger than the solvent molecules. So that the molecular motion of the solute resembles Brownian motion through a viscous media. So it resembles in a viscous medium. So those are some general assumptions. Also, there are other assumptions which will be evident through the modeling. For example, it's like solute particles are under force balance. Okay, now let's look at the model. So let's look at the Stokes part. Flow. So what the Stokes flow says that if you have a spherical object, let's consider a spherical object of radius a moving at velocity v at velocity v infinite. Infinite doesn't mean the velocity itself is infinite. It's just a symbol, means it's the velocity compared to the infinitely larger domain of like stationary fluid. That's what it means. Well, at infinite, at a velocity infinite through a viscous fluid, through this was a fluid of viscosity. So Stokes say that if there such things happens, then the viscous drag force, the force is a vector. The viscous drag force applied or exerted on the sphere due to the flow is 6 pi mu a infinite. So this v is a vector. That's why the viscous drag is also a vector. So I'm trying to change my notation. So let me change this pi. This pi is, I'm writing in this way. Okay. If I'm writing in this way, this means the constant pi. If I write in this way, this means osmotic pressure. At least for this lecture, I may forget about this notation in other lectures, or in the lectures that doesn't cause a confusion of these two pi's. I may just use a random pi, but now for now, it matters. So I'm going to use this. Now what Einstein says. Einstein say that okay, for particles under osmotic pressure. So osmotic pressure is we know that is pi RCA. Sorry, is RTCA. So if there's an osmotic pressure gradient, for example, if you have particles, which is high concentration here and a low concentration there. So for each particle, let's say this particular particle, because it has the tendency to move from left to right, it feels like as if there is an effective osmotic pressure or effective force due to the concentration gradient on this particle, because the particle would like to move to the right. So like this is sort of like a pseudo force. There doesn't exist such force, but you can think about effectively, there would be a force that try to push the particle forward. So in that case, the force due to this osmotic pressure difference, which is minus 1 over NaCa delta pi. Okay, now we have another Na. This Na is not a flux. This Na is Avogadro's constant. I wonder how can we differentiate N versus a flux? If Na is a flux, then it should be a vector. I would put a vector sign of it. Then you might say, okay, if Na is a scalar, it's just a flux along the one direction, then I usually would say NaZ. So if you recall from previous lecture, if we are saying if it's along the one-dimensional flux or it's a boundary condition along, for example, along the y direction or along the z direction, I would use NaY or NaZ. In that case, it's a flux. If it is Na itself without x, y, z, then it should be, the total flux should be a vector, then I would put a vector sign on it. If it doesn't have a vector sign, then it's Avogadro's constant. So you can think in that way, if that helps. Otherwise, if not, you can figure out from the context of our discussion. But here I'm telling you, in this context, this Na is Avogadro's constant. So if you put the pi RTCA, you will get minus RT let me see, NA QA gradient of CA. So let's draw this. So let's say if this is the velocity, maybe let's not draw velocity. Let's draw velocity here. Let's say this is the velocity of motion. Then the force, the magnitude of the force, which is or just the force, which is like this force is due to the osmotic pressure gradient. On the other hand, you would have a drug. We should have an active sign because the drag force is always opposite to the direction of the drag. Drag force is always opposite to the motion of the sphere. So the drag is to the negative direction. So the reason I'm drawing here is because let me put it in this way. Okay, if I draw the area of the force, it means I've already considered its magnitude. Then I don't need to put the area. And if you are considering writing force all along the one single direction, then you need to consider like it's positive or negative. But right now, if you just draw a free body diagram, like if the sign confuse you, you don't need to worry about how your convention of direction is. You just think about a particle and think about this particle move from left to right. So you know that the drag force is to the left. And also the force, which is due to the osmotic pressure, would be to the gradient. Like this is negative of the gradient because it's always against the gradient. It's always from higher concentration to lower concentration. That's why we have this force. So under force balance, basically it tells you like the total force acting on the object will be zero. So that means F drag plus F due to this osmotic pressure. Let's call it osmotic pressure. So that means minus 6 pi mu A V infinite minus R C N A is zero. Okay, you rearrange it to solve for V infinite. So you will get V infinite equals to minus RT divided by 6 pi mu A NA CA gradient. Okay. Now the next step is we are looking for the flux NA. Now here this NA is not Avogadro's constant. This is flux NA. Flux NA would be, in this case, you are thinking about this is important. You are thinking about a single particle. Let me see. Let me just draw again. You are think about a single particle, and because it's dilute, this single particle doesn't interact with other particles, and for itself, when we talk about the flux, one single particle doesn't diffuse. Diffusion is a phenomenon of a collection of particles. This is like a thermodynamic behavior of a collection. Then you would say, okay, diffusion happens from high concentration to low concentration. But if you only have a single particle, like if you are throwing a baseball or football or basketball, but whatever ball you are throwing, it's a single ball. If you are asking what's the flux of the ball, then you would think about directly what's the velocity of the ball. So that's what you would think about. Then in that case, you would think from the convection instead of diffusion. So the flux of this particle, then if you think about a bunch of particles, although our analysis starts from one single particle, but now you think about every particle does the same thing, then the flux would be the velocity of the particles multiplied by the concentration of the particle. Then you would have Ca multiplied by this expression of Barty. I mu A N A gradient of Ca. Now this is the molar flux. This is molar flux. The logic is that here we figure out the molar flux by considering individual particles. We are assuming individual particles is under convection. And now you zoom out, you are looking at, okay, now we obtain this is the flux. What if this flux is due to convection, due to the diffusion of the solution of the solute in the medium? So the difference is when we derive this equation, we look at the individual molecule, and then each individual molecule is convected by itself. You can think about in this way. If a molecule has this velocity V naught, or if you throw a basketball, the basketball, you give it a velocity V naught, then it will move at that velocity. So that's how you calculate from individual particles. Now collectively you are saying, okay, let's look at the entire solution. Now we have so many particles move at a certain flux. If this is due to diffusion, then the flux should also be given by this equation, DAB delta CA. Then what you are going to do is you compare these two equations. And then you get a conclusion that you can approximate or estimate the DAB as RT divided by 6 pi mu A NA. Well, I is ideal gas constant, T is temperature and pressure. Mu is the viscosity of the water. A is the radius of the particle of the solid. And this is Avogadro's constant, of course. This is called the Stokes Einstein equation. Equation for estimating the diffusion coefficient. All right. So hopefully you can appreciate how helpful this equation is historically. Because well, this is just an approximation. In reality, it's much more complicated because these approximation had a lot of assumptions. For example, we assume it's dilute, we assume the solute are sphericals. Well, in reality, nothing is no proteins or any particles are perfectly spherical. And a bunch of assumptions. Sometimes assumption can be broken. But in many cases, we will assume these assumptions are valid for the problems we are going to solve. And that's why we can use the Stokes Einstein relation to approximate the diffusion coefficient. So you only needed to know the viscosity of the medium, the temperature, and also the size of the solute you are looking at. Then you are going to solve it. And then let's look at some viscosity. So here I'm just going to give you some numbers. You can write down in your notes. You may use it in the future. So viscosity of water. It is a function of temperature. So it is 37 degrees C. The viscosity of water is 0.691 centipoise. So recall 1 centipoise is 10 to the minus 3 Pascal second. So at 37 degrees is this temperature, and at 25 degrees C, the viscosity is 0.98 centipoise, and at 20 degrees C, the viscosity of water is 0.002 centipoise. So we roughly say at room temperature, the viscosity of water is 1 centipoise. But in the body, it's a bit lower because of this. And let's also look at the Valerian plasma. The viscosity is about 1.2 centipoise. So it's a little bit higher than the viscosity of the water. Okay, this is something you can just accept as a fact. Oh, by the way, you don't need to remember this, although the exam would be like close book, close notes. But if you need those numbers, anything which is like considered as a part of that table, I would give those numbers to you during test. So don't worry about these things. You do need to remember equations. Those, for example, fixed first law, these type of things, you're expected to know these by heart. But for those like constant numbers, like what is the ideal gas constant, what is Faraday's constant, these will be provided if you need them in tests. Okay, now let's see. In reality, if you solve a real life problem, you are finding a protein, and you want to know a protein or amino acid, their diffusion coefficient in water, and if you want to check their size, radius, it's less likely you will find them. Well, maybe you can find them in a handbook, but most likely what you will be given are the molecular weight. So let's see, estimate, how do we estimate the radius of a particle given its molecular weight. So molecular weight is usually written as MW. The units by convention is gram per mole. So the conversion between radius and the molecular weight is radius equals to 3 times molecular weight divided by 4 pi rho NA. Pi is 3.14. The NA is Avogadro's number to the power of 1/3. So this rho is the density of the particle. And in most cases, we would approximate all particles that have a similar density, 1 gram per meter per centimeter cube, the same as the density of water. That's what we are going to assume for the purpose of this class. And then once you know, if you are given a molecular weight, then you can use this equation to figure out what is A, and then you can use Stokes Einstein relation to figure out what is the diffusion coefficient of that particle in water. So now let's look at another helpful relations. So if you know, so let's say for a given particle, or for a given species of solid, if the diffusion coefficient is known at a reference temperature T1 and a viscosity mu1, so if viscosity, or if the diffusion coefficient EAB at condition 1 is known at a temperature T1 and the viscosity mu1, then at T2 and mu2, we can find corresponding diffusion coefficient by this relation. DAB2 equals to, well, DAB at condition 2 equals to DAB at condition 1, multiply the ratio of mu1 divided by mu2, multiply the ratio of temperature 2 divided by temperature 1. So the T is the temperature of the system of the solute, and the mu1 is the viscosity of the solute. So this is the easy relation we can find. Okay, let's look at some examples. A solution has molecular weight of solution. It's 180 gram per mole. We know that it's spherical shape. And the density is given. Even if it's not given, you can just assume it's the same as water. So 1,000 kilogram per meter cube. Estimate its diffusion coefficient in water at 25 degrees C. So for this problem, it's a generic problem. It's also a very realistic, like a real life scenario. If you are interested in a molecular weight, and you look at a table, it tells you it's 180 gram per mole, and you also know its density. That's all you have. You have a particle at your hand, or some particles at your hand. And then now you are working at a room temperature, or work in water at 25 degrees C. You want to know what's its diffusion coefficient. And here you can use what we learned today to solve this problem. So first of all, you need to know the size. If you want to use the Einstein relation, then you need to know the size of the radius. So let's first find out the size. Find size first. So A equals to 3 molecular weight by 4 I rho M A to the power of 1 and 3. And we plug in number. 3 is 3. 3 multiplied by it's gram per mole. If we want to convert to SI unit, you want 0.18 gram per mole. For pi, and the Avogadro's number is 6.022 times 10 to the power of 24. Now you can see the per mole cancels from the numerator and the denominator. The kilogram cancels. You're left with meter cube. And then if you take the power of 1/3 of meter cube, you get a meter. Okay, that's good. Indeed, you get something of dimension length. That's what you need for the radius of a sphere. That's good. Okay, then you just work out on the numbers. You will get it's approximately 4.16 times 10 to the power of minus 10 meter. Okay, now let's use Einstein equation. D RT divided by 6 pi mu A. Okay, R is 8.31 joule per mole per Kelvin. Okay, the temperature. So in all the physics problems, the temperature is the absolute temperature in Kelvin. You never use Celsius. You never use Faraday's. It's always the absolute temperature. So at the 25 degrees C, it is 289 level. They have mu. Okay, if you look back at the number we give at 25 degrees C, the viscosity is 0.89 centipoise, which is 0.89 into the power of -3 Pascal second. Then the radius is 4.16. Also have Avogadro's number 6.022 times 10 to the power of 23 per mole. We have per mole cancels up and down. The Kelvin cancels. We have let's see, in the numerator we have joule. Joule is Pascal multiplied by meter cube. Now you have a Pascal in the denominator, and then you have meter in the denominator. So you're left with meter cube per second, which is exactly the correct dimension for diffusion coefficient. So that's also good. You have at least you have done some sanity check. Okay, if you work out the number, it will give you 5.9 times 10 to the minus 10 meter square per second. Okay, that's the diffusion coefficient. Let's look at it. Diffusion coefficient of water. No, not water. The diffusion coefficient of glucose in water. At 25 degrees C is 6.7 into the 10 times 10 to the minus 10 meters squared per second. estimate coefficient at 37 degrees C in water. So this problem is given in the format that you know the diffusion coefficient under one condition. You want to find its diffusion coefficient in another condition. So we can use the equation we earlier. So you have DAB at the condition 2 equals to DAB at the condition 1 divided by mu1 divided by mu2 and multiplied by T1 divided by T2. Sorry, T2 divided by T1. Now we plug in the numbers. So DAB1 is given 6.7 times 10 to the minus 10 meters per second. Okay, let's see what's mu1. Mu1 is at the condition 1 is at 25 degrees C. If you look at the number we just discussed earlier, at 25 degrees C, the viscosity is 0.89 centipoise. Now divided by mu2, which is at 37 degrees C. At 37 degrees C, the viscosity is 0.691 centipoise. Now the T2 is at the new condition is 37 degrees C, which is corresponding to 310 Kelvin. T1 is the first condition, 25 degrees C. It's 298 Kelvin. All right. It will give you 8.97 times 10 to the negative 10 meters squared per second. This is the diffusion coefficient. Okay, so let's leave some exercise for you guys. One for today is let's derive the expression for the ratio of let's just derive the DAB2 equals to DAB1 multiplied by mu1 divided by mu2 multiplied by T2 divided by T1. So derive expression for the ratio of two diffusion coefficients in a liquid. Same to different temperatures and viscosities. Basically, you're just going to derive y DAB2 equals to DAB1 omega 2 minus T2 over T1. And exercise 2 for this lecture. Okay. Games A and B have molecular weights. A solvent gram mole and 150 solvent gram mole respectively. Assuming equal shape and density. Well, the equal shape means they are spherical. Like assume same density. So compare their diffusion coefficient. So your task is to compare. Diffusion coefficients. Okay. That's all for this lecture.